T. So you need to basically draw random pairs, calculate the difference, and you do this for samples of a known size. So we had with the single sample SEPT test, for example, we had these hypertensive male smokers and we measured their cholesterol levels. So we had a sample of 25. That's one sample. Now we take out 20 of these samples, we get 20 different sample means, and that's our comparison distribution. With the paired sample t-test, we had again samples of 25, for example, and we had before and after, we had these differences. So our comparison distribution was the differences, the mean differences of these samples. Now we have sample pairs that we're basically drawing from both samples at the same time, and we get one sample based on these random samples drawn from each of our tested samples. And these differences again build each of these means, that's the mean difference of these randomly drawn pairs. Each of these are samples that contribute one mean to our comparison distribution. And this is very hypothetically, but it holds true in the greater realm of things. And this comparison distribution of the differences between means will essentially then allow us to test for the hypothesis against a difference of 0. No chronological order and 2 absolutely independent samples. Any questions, or was that somewhat clear? So again, you have 2 samples, you draw random individuals out of these 2 samples, you create one difference, you keep the difference, you drop the participants back, and you create the first sample. The first sample gives you one mean difference. That's one of these squares. Now you do the second sample, and you create again a sample of 25 differences. You randomly pick out participants, you create one difference, keep the difference, drop the participants back. You get another sample of 25. That's the second square. And you repeat that. And by that, you get a comparison distribution of these differences between means. And that will allow you now to essentially standardize the differences that you have observed and compare it using the same approach we have done by calculating a t to the reference or the null hypothesis of 0. So the 6 steps for hypothesis testing are again the same. We're identifying the populations, we're identifying the distributions and the assumptions. The assumptions, most and foremost, is normal distribution, random sample, generalizability, independent samples. So there are 2 independent samples at this point in time, and they're not associated with each other, and these need to be met. Then we state the null and research hypothesis, where again, under the null hypothesis, we assume that there's no difference between the 2 samples. Under the research hypothesis, there is a difference. Again, this is a 2-sided test, so we assume 2.5% of type 1, potential type 1 error on each side. Same concept applies. Then we determine the characteristic of the comparison distribution. So that's basically where we take our estimate of that variance. And this is, I keep on talking about the variance. We have 2 variances in both groups. What we need to do to estimate the variability of this comparison distribution, we need to pool the information from both sample variabilities. We need to pool them together and create a pooled variance that we will use for the standardization of our distribution, our comparison distribution. And this is what we're doing here, because the steps here are going to be the same. We're estimating our variability of each sample. We're pooling this together, and this pooled variance that we'll calculate today is essentially then to be, again, used to estimate the actual standard error of the mean, so the variability of these means. And this will then allow us to standardize based on the standard error of the mean. Once we have characterized the comparison distribution with the standard error of the mean, we're estimating the critical values. We'll determine our cutoffs with the t-score distribution table. Then calculate the test statistic, which is slightly different from last time, but still follows the same context. And once we have our test statistic, our t, we make a decision in the light of the critical values that we have determined in step 4. So today's example is essentially dealing with two different, I hate to call it a population, but they're labeling it as population. It's a sample, right? It's a sample population. So we have two different sample population. So you know how being a wine connoisseur is actually, it's people do that for a living. So there's a lot of enology. That's actually that's the art of knowing how to taste wine and the science behind tasting wine. That is not always the case. So if you tell somebody they're drinking wine from a $90 bottle, although you give them a $10 bottle, there's a good chance they're actually gonna rate the wine better just for the sake of this being labeled with a higher price. Believe it or not, that's the thing. So now we have two samples where so same wine, both samplers get the same wine. Population 1 is being told it's a $10 bottle of wine. Population 2 is told it's a $90 bottle of wine. So now essentially we are looking at the rating under the null hypothesis that there's basically no difference because it's the same wine, right? And we are testing this and we're seeing whether there's a significant difference in their rating based on the independent variable, which is here, the price tag on the bottle. So the price tag on the bottle has two different levels. One is $10, one is $90. And this is the comparison we're going to do today. So I didn't come up with this example. I find it a good example, but it's quite unconventional. But yeah, so this is the comparison we're going to do today. So we have now, first, we know now what our populations are. We know now what the comparison distribution is because the distribution of the differences between means is exactly that comparison that we're going to do today. So again, we have these two populations. We're drawing out pairs until we have a sample of 25. We're dropping these always back. Then we're repeating this and we get a difference between means that essentially becomes our comparison distribution. And we're comparing this comparison distribution against a change of 0, which is essentially our null hypothesis. So assumptions are basically, so we don't really know whether the population is normally distributed. There's a good chance it actually is, but we don't know that. So this is to be approached with caution. Participants were not randomly selected, so it could be that in one group, you have, I don't know, a group of sommeliers, whereas in the other group, you have people who have no idea about wine, drink wine for the first or second time in their lives. So in that regard, you got to be very careful in terms of generalizability and generalizing your findings. Makes sense, right? Any questions about the example? I think it's a fairly simple example, right? So the repetition here becomes when you're confronted with a question like that and you're facing a question like that, first, I would kind of read very carefully how many populations do we actually have. If there's only one population, then it's simple, right? If there's only one population and you're comparing this to one reference value, be it the population mean or be it, I don't know, any reference value of any kind, you would think either it's a STAT test or a single sample t-test. The distinguishing factor here is, do I know the variability of this population? Do I know the variability of the population? Or do I have to estimate it based on the variability in my sample? If I have to calculate it myself from the sample, I'll think of a t-distribution which resembles the normal distribution of a population and estimates this variability. If I know the standard deviation or the variability of the population, I use a STAT test. Or if I have a sample that is very large, I might get away with a STAT test and I don't need to resort to the t-test. If I have two samples, I need to understand, is there chronological order to it? Do I have a before and after situation? Is it the same individual at two different time points, or is it the same individuals at two different time points? If so, I would go to use a PL sample t-test. If it's two different participants, the two different samples from different participants, I would resort to an independent sample t-test. So again, the STAT test, you're testing a distribution of means. That's your comparison distribution. Same with the t-test, which essentially both will be standardized using the standard error of the mean. If I have a distribution of mean difference scores, this is the paired sample t-test. I calculate this difference and I use this distribution of this difference scores, of this mean difference scores, as my comparison distribution. And for the independent sample t-test, I have the distribution of differences between means. So again, random samples, I create this random samples of differences, and I get a certain number of these differences, and now we're learning how to estimate this variability. So null hypothesis here is that people that are told they're drinking wine from a $10 bottle will give it the same rating as people drinking wine they are told is from a $90 bottle. So sample mean 1 equals sample mean 2. I am somewhat reluctant to call it a mu because it's not a population, but I'm assuming that the sample means are reflective of the actual population mean. The research hypothesis, on average, people drinking wine they're told is from a $10 bottle will give it a different rating than people drinking wine they're told is from a $90 bottle. So this research hypothesis would imply that sample mean 1 is unequal to sample mean 2. Consequently, mu 1 is unequal to mu 2. So, and there are a couple of more steps this time around. So determine the characteristic of the comparison distribution. With two samples for an independent sample t-test, it is more complicated to calculate the approximate measure of spread, which is true because we have two different samples. We're drawing out individuals and we're calculating these differences and the distribution of these differences between means from two different variances. So this pooled variance we need to calculate is essentially affected by both sample variabilities. So therefore, we calculate the variance for each sample first, and then we use this sample variance to calculate a pooled variance. That's basically an aggregated version of a variance that allows us then to standardize our comparison distribution affected by the variability of both samples. And we will learn how to do that. Then we convert the pooled variances from the squared standard deviation by dividing the pooled variance by the sample size. That gets us to a standard error of the mean differences, right? Then we're adding these two variances because they're contributed for both our samples, and we're calculating the square root of this form of variance. And that's where we're starting Excel. So you have today an Excel spreadsheet that basically shows exactly that. So we have that example that Nolan and Heinz will calculate today. And we have here $10 bottle of wine and the $90 bottle of wine. So let's start by calculating the average. Oops. Let's calculate an average. So that's simple, and we know already how to do that. That's the average function. And we can do the same thing. Make sure to select all cells. Actually, with the other class, I actually had a hiccup. I would copy this function over there. Keep in mind, if you only select 4 and you copy it over, it will only take 4 cells. So that was actually kind of an interesting mishaps last time. So you need to make sure that all 5 cells are selected in your average function. Otherwise, you would be fine to just drag it over, because then it becomes 3.7 instead of 4. I'm just flagging this because these are mistakes that could happen to you in real life. I don't know what you want to do in your walk of life later on, but you basically use Excel. You remember that there was a statistics professor who showed you how to propagate functions and in Excel, and you do it, but you really need to individually pay attention that all cells are collected in your function. So if you do the same thing now with the, Exactly, yes. So this is the rating, this is the respective individual rating. So these are two samples. We have one sample with 4 entries and we have one sample with 5 ratings. And these ratings, that's a very good question, because that's what we're going to do today, because you have unequal variances.
So the whole experiment is really not a good one. Aren't you meant to have the same amount of people?
Not necessarily, you don't. Well, in a perfect world scenario, yes, you would have the same number of participants. But think of conducting a randomized controlled trial. You basically have 150 people that you follow over the period of a year. People move away. People just look at you like, you know what, I did this 3 months. I don't want to participate in your study anymore. So people drop out.
Then you would have to drop people from the other side.
No, you can't do that. No, because how would you drop them? It's not wrong what you're saying. It's not wrong what you're saying. I'm totally disagreeing that analytically it would make sense to do that. And, but you also diminish your sample size. You diminish your sample size and you harm your power, right? So it's easier to deal with this analytically. And the independent sample t-test allows you to deal with that. And that's the beauty. You're right, because the independent sample t-test you can do a test which is assuming equal variances, which is more likely to be the case if you have the same sample size. I agree. Or you can do unequal variances, which is what we're doing today, where you account for these differences and the mismatch in sample size. Excellent question. Thank you. Okay, so now we have the standard deviation. That's basically any other questions. So if we do the standard deviation, you do STDEF.S or just a regular standard deviation function. You just select these 4 entries and you do the same thing for these 5 individuals. So you see already, just like we expected, there's a difference in the sample size, and now we have differences also in the standard deviation. Yes.
You do .s sample.
Yes. Of note, if you don't do the S, it's still the same function. So by default, Excel uses for the STDEF function STDEF.S. So it assumes there's a sample and it does the correction for the variance estimation. STDEF, yes. Yep. So that's a different approach. So, but now, as you correctly lined out, so there's a difference in the degrees of freedom. So we have for a degree of freedom of 4 individuals, we have 4 minus 1, which is 3. And then we have for 5 individuals, we have 5 minus 1. So the degree of freedom here is 3, and the degree of freedom here is 4. So now we need to deal with this somewhat analytically. This. Okay. So we have degrees of freedom of 3 and 4. Now we need to calculate something. You know how to calculate proportions, right? So we have now a degree of freedom 1. We have a degree of freedom 2. And logically, we have a degree of freedom total. So our degree of freedom total is nothing else but the sum of 3 and 4, which we know is 7. That's simple. But it makes a difference analytically because It's an uneven number. So now we need to calculate our, I keep on calling it aliquot, but let's call it proportion df. So we have now for df1, we have now 3 divided by 7, right? Then we have for degree of freedom 2, we have 4 divided by 7. And that obviously needs to add up to 2. To 1. 2. Needs to add up to 1. So, yes.
What you did for the proportion.
Yes. So you have a total degree of freedom. So the sum of both degrees of freedom gives you the total degrees of freedom. So that's in both samples, that's how many individuals you have. So now the proportion of these is basically the proportion of the respective degrees of freedom as a proportion of the overall degrees of freedom.
3 over 7.
3 over 7 and 4 over 7. Yeah, let me actually. So this is, let's do this. This is 3 over 7, and that's 4 over 7. So that's where we're starting off. So this is what Noren and Heinzen does here. So they're squaring it. So now we are, so from the standard deviation, we come to the variance. I didn't do that yet. So this is equal VAR is the variance function. Oops. Now we get our variance. VAR is now the second one. Good. So, and now we're getting to the actual calculation part. So what do we have? We remember the calculation of the standard deviation, or the precursor of this. We have here in the numerator, we have the sum of the squared deviations that adds up to our numerator. In the denominator, we have our degrees of freedom that gives us the variance. So now we're calculating pooled variance. We're not employing the square root, which gets the variance to the standard deviation. No, we're staying on that level of the squared version, and we're working with the variance. So now this degree of freedom, this proportion will now be used to distribute the weight to the respective variance of the respective group. So we have a total of 1. So that's 100% of variance. If we have now a proportion, as in our case, we have, what was it, 43 here on the sample 1. We have 57 on sample 2. So now we're basically aliquoting this to the respective group. So if we take the variance, we're calculating now our variance, the weighted variance. It's a weighted variance. Weighted variance. We're calculating this now by taking our variance of 0.65, multiplying it by our proportion. That's 0.27 or 28. Now doing the same for the weighted variance of sample 2, multiplying it by our proportion of 0.57, gets us this weighted variance. So now from the weighted variance, we get to the pooled variance. And we're calculating now the sum of these two. The pooled variance is 0.84. So this essentially gets us now to the next step. So we will need to next add these two variances up. And we're doing this by dividing it by our respective sample size. So our standard error of the mean estimate is now our pooled variance divided by our sample size. Don't forget, usually we do a standard deviation divided by square root of the n, right? That's how we calculate, according to the central limit theorem, our standard error of the mean. Now we're doing it different because it's still squared, so we can divide it only by the sample size. We don't need to go for the square root. So our actual formula, our actual calculation is now, so this is our SM, or our SEM. Our SEM is now our pooled variance divided by the sample size, which is this plus 1. So this is, we calculate the degrees of freedom. Now we're calculating back to the sample size. It needs to be the sample size, don't forget.
5 plus 1.
Because I used in the formula, I used the degrees of freedom. Degree of freedom is sample size minus 1. I'm just calculating it back. I'm just adding 1 back. I know it's a little complicated, but I don't have another cell. Well, actually, you're right. That's not. Okay, let's add 1 line. N is now 4, and here it's 5. Okay. Okay, let's do pool variance divided by, oops, divided by our N plus the pooled variance divided by our N of sample 2. That gets us to a standard error of the mean . So that's our standard error of the mean. That gets us on this standard error of the differences of means. Employing the square root will get us to what we know as the standard error of the mean. So this is actually the standard error of the mean squared. So now the standard error is basically the square root of this. So that gets us, yes.
On the formula thing, on the PowerPoint.
Yeah.
First formula, that's the weighted one. That's the weighted.
These,
No,
this one, that's the regular variance.
that's regular variance.
That's regular variance. That is variance. If it were under square root, you basically would look at the standard deviation. So this is just variance. And then you basically take this variance of the respective sample, you multiply it with your proportion, right? That's the proportion. And then you basically bring this pooled variance into the respective shape to add them. So it has 2 different parts. This is a weighted variance by dividing it by the sample size. Well, we do have, well, okay, poorly expressed, sorry. It is now, this would be a weighted variance, right? These 2. You're adding these 2 weighted variances to basically get to a pooled variance. And then you utilize this pooled variance twice by dividing it by the sample size to get to the 2 independent standard error of the means, which you pooling together, then you're adding them, you're merging them, and this gets you to your standard error of the mean squared, and then you get to the standard error. And that square root gets you to the standard error. That's how you get the standard error. And this is the standard error that you correct of this square here. So that is adds up. And so now we're getting to a different discussion. So this is a different animal now. So we have now the calculation of our t would then logically be, you remember with the paired sample t-test, we had the mean difference minus 0. So now our mean difference is now mean x minus mean y gets us a difference, right? And then we're subtracting, in a second step, we're subtracting our null hypothesis. And our null hypothesis here is 0. And then dividing it by the standard error of the mean, obviously. But this would be assumed 0 because our null hypothesis says that there's no differences between our two sample means. So now this minus 0 drops out, and then the final formula is here mx minus my divided by the standard error of the mean. That's how we conceptually approach it. If you have a hypothesized difference, you would basically subtract this hypothesized difference from m minus my, mx minus my. But we don't. We use a null hypothesis if there's no difference, and this is the final formula that we're using. But nevertheless, I bring this one into the spreadsheet. So we're basically bringing this now in the spreadsheet. And that basically allows us now to estimate our t. So our t is now mx minus my. And this we know is mx minus my divided by our standard error of the mean. So that's basically our t. So we have a t of minus 2.44. Now we just need to calculate the critical t, or find it in our t-score distribution table. So we have a total degrees of freedom of 7. Remember, we have 4 in one group and we have 5 in the other group. In total, this is n. Total n would be 9. Minus 1 for each group is minus 2. It gets us 7. 7 with a 5% alpha is 2.36. .36 is basically our critical t, and minus 2.44 exceeds our critical t on the left side, on the negative side. Therefore, we are rejecting our null hypothesis. Make sense? Everybody with me? Any questions? Yes.
Can you scroll back up so I can see what it was in your outflow? What was in your,
Which part?
when you started plugging in the numbers for the T formula?
That's this one. So we're calculating. Okay, so once again, so this is basically it's 4 minus no, it's what is it now? It's 2.5 and 4. So that's minus 1.5. So of note, if you calculate now x minus y, it's the same as calculating y minus x, right? Same principle. Same principle, T is the same, it's a two-sided test. Only if you have a directional hypothesis, which hypothetically you could do as a one-sample t-test, not one-sample, a one-sided independent sample t-test. Hypothetically, you could do that. It's rather a rarity, but you could hypothetically do that. Then the direction would make a difference. So basically, let's recap. So we're calculating our variability for each sample. We get the standard deviation. We're using the standard deviation to basically get to the variance. We're calculating a proportion of the degrees of freedom, and we're using this proportion to essentially calculate weighted variances for each of these two samples. We're adding this up, and we get to 0.84 as our pooled variance. Next, we calculate a squared standard error of the mean by basically adding the pooled variance divided by the sample size to standard error of the mean of the first group plus the standard error of the mean of the second group gets us to a pooled squared standard error of the mean. Employing the square root on this pooled standard error of the mean gets us to a standard error of the mean for our comparison distribution. Utilizing this in this formula, utilizing this in the formula mx minus my minus our null hypothesis of 0, dividing it by the standard error of the mean, will get us to a t. And this t is basically then being used to compare against the critical t, which basically leads us to reject the null because it exceeds our critical t of, in that case, to the left, it would be minus 2.36. Any questions on this? I think it's quite simple. The concept is a little tough, but it's overall it's not that complicated. So now this is the comparison distribution. So we have our differences between means. And we have now 2.37 as 2.36 as our threshold. Now we know that our differences in wine rating is actually exceeding on the negative this value. So we have a t that is mx minus my divided by our standard error. Minus 2.44. What is important to keep in mind is that when you want to report statistics, you have to follow a certain nomenclature. So one way to do that in most cases, because with t-distributions and t-tests, you don't really have an exact estimate of your p-value. You could have a very detailed p-value. And that's actually, so there's an Excel formula that would allow for you to kind of do that. And so the exact p-value can be calculated with the t-test function. And I just want to spend a second to do that. So if we open for t-test the formula builder, we have in array 1 and array 2, it asks us for the number of tails and it asks us for a type. So array 1 is simple, right? That's our sample X. Array 2 is our sample Y. Tails is now the number of distribution tails that can be either one-tailed or two-tailed. Depends where you want those 5% of acceptable type 1 error risk to go. Type is now essentially either it's a either it's a paired sample t-test, and we have, I believe we did that test with the paired sample t-test, or it's an independent sample or two-sample t-test, which can be either equal variance or unequal variance. Of note, here you have in parentheses, and we will talk about this when we get to regression, we have the word homoscedastic versus heteroscedastic, which is unequal variance. Homo equal, hetero different. So it has an equal variance or a different variance. Scaticity is the actual distribution variability. So if we have now a two sample unequal variance, that's 3. So array 1 is here $10 wine, our 4 participants. Array 2, our 5 participants here. Tails is 2, and type is 3. If we're clicking on done, we're seeing here a p-value of 4.1%. And these 4.1%, that's our rest type 1 error risk. Yes.
What did you do about, where did you go to and leave them? For tails, how did you-
Tails is 2, right? It's a two-sided test. 3 is when you look here at type, it's either with 1, it's paired. With 2, it's homoscedastic or equal variance, and with 3, it's unequal variance, heteroscedastic. So that gets you to the p-value. So this is our corresponding p-value. So if you wanted to report this in a paper, for example, you can do our T for a degree of freedom of a known size. You would report this as a T7. Where you have a calculated T of minus 2.44, oops, of minus 2.44, semicolon or colon, and the P of, oops, P equals 0.04. Another way is T7, that's what Nolan and Heinz suggest here, because with a T-score table, you would not quantify the p-value directly or exactly. The way how to quickly do this is by just say it's smaller than 0.05, which is your alpha. Comes to the same thing. So if you're only interested, is it smaller than the alpha, you just say it's smaller than the alpha. So that's basically how you would report that. So that's how you can add it to a journal, to a master thesis or whatsoever. Good. Okay. Any questions on that, on the reporting? So it's really the p-value per se. Since we're doing hypothesis testing, where we're either rejecting the null hypothesis or accepting the null hypothesis, it really does make a difference what the p exactly is. If you dig a little deeper, it is not entirely uninteresting. It becomes more interesting the deeper you go into the statistics. Because that alpha that you have selected is basically an arbitrary alpha, right? It's like there is no real reason why you would embrace 5, except for that in the 1960s, a statistician named Fisher said like, oh, 5% sounds reasonable, let's do that. Since then, the entire community has embraced 5%. For various reasons, you would actually use smaller alphas, particularly when you deal with large sample sizes. So in the same fashion as we did with the STAT test and the t-tests, we can calculate confidence intervals, and they're calculated in the same, well, we know already how to calculate those, right? It's like, so essentially, the way how you do that is, so let's do 95% CI. It's the same concept, so you have a lower limit and upper limit. The lower limit is basically the way you would express this. Oh, well. So it is, you need to calculate first your average minus the second average. Then for the lower limit, you need to subtract your critical value, your critical t, multiplied by your standard error of the mean, which is a 0.61. So that gets your lower limit of minus 2.95. Same story with the upper limit. This is mean of x minus mean of y minus 2.36 multiplied by the standard error of the mean. Oh, minus, plus. It's late. It is late. Okay, same concept applies. If you have a lower and an upper limit of your 95% confidence interval, you will always keep to have in mind. So this is a characterization of your comparison distribution. So if your 95% confidence interval does not contain 0, that means that your estimate is basically a statistically significant difference. So you basically, this would be the bounds of your 95% confidence interval, right? So if your actual, so if you do it around the minus 1.5, this will basically exclude 0 as your null hypothesis. So here's the right depiction. So you have here basically your null region, and here you have your critical region. So if your actual 0 is out there in the critical region, you're basically rejecting the null hypothesis. Any questions on this? That's quite an important concept. So we have minus 2.96 to minus 0.04. And this basically leads to confidence interval. So lastly, we're also calculating effect size, which is calculated in the same format as we did before. What's important here is, here you need to go back to actually your pooled variance, and you need to square root your pooled variance to get to that pooled standard deviation. So your t calculation is actually then your mx minus my, so 2.5 minus 4 divided by the square root of your pooled variance here, 0.84. So that gets you an pooled, it gets you a d of minus 1.63. Just for the sake of simplicity, let's set this to absolute. This 1.63 indicates a large effect size, right? All right, so that was the calculation of d. Any questions on this? It's simple, right? It's once you know all the steps and you know how to calculate the pooled variance, then it's just understanding the concept that you need this from both ends. You need to pool this in a weighted fashion. You need to add this together with contribution and weights from both of these samples, and that basically gets you to an overarching pooled variance, then to a standard deviation, if you need it, or from the pooled variance, you get to a squared standard error of the mean, and the standard error of the mean ultimately. Good. Okay, that was the example. So what do we conclude out of that? If you're serving a wine where you tell everybody that's a $90 bottle of wine. They will just like the wine more. Good to keep in mind for hosting dinner parties, right? So, okay. So we have now the effect size. We know those conventions. We have 0.2 to 0.5 is basically a small effect size. There's an effect size present, but it's small. We have 0.5 to 0.8 is medium, and greater than 0.8 is large. And then the last point, and I don't want to go too deep into this, but it is important to keep in mind. So Bayesian statistics. So whenever thinking of hypothesis testing, you're making a dichotomous inference. So you say, okay, my null hypothesis is wrong. I reject it. There's a difference between these two samples. That is just like we had in the context of confidence intervals, one possible approach. You can just say, okay, so I have a significant difference and I'm accepting the significant difference as being significant. And I basically, I reject the null hypothesis. With confidence intervals, we had the argument with the differences between biological sexes and mathematically performance. We found papers that rejected, and that meta-analysis of Feynman basically showed that there may be subtle differences in certain tasks, but the overall distribution and the bell shape and the entire bell of the bell-shaped distribution basically was still overlapping to a large extent. So that difference is maybe true in some of the extremes and in some certain tasks, but overall there's not significant, they're not substantially different from each other. Same applies with comparing samples, because if you include in your hypothesis testing a prior belief, you also gain a lot of information out. So that means that prior beliefs will basically change the way you're looking at the probability of this actually being significantly different. Let's assume we would not have seen a significant difference with our wine drinkers, and they would have known that the host basically always buys wine that doesn't cost more than $10. That would inform our comparison and would render our results that we've seen, our significant differences, not as meaningful, and basically puts a whole different light on what we have seen. So that basically is a Bayesian approach to some extent, because prior belief informs how we're interpreting our hypothesis test. Or for example, I made the statement that alpha levels are chosen differently when you have a particularly large sample size. So if I know I have a very large sample size, I may choose a priori greater alphas to make sure that I am not committing a type 1 error, because that prior belief of knowing it's a large sample size and I'm more likely to reject the null hypothesis with large sample size will essentially inform the value of my hypothesis test. Another example, which is nowadays, I think each of you has heard about diagnostic accuracy. We made it through a pandemic, right? And everybody talked about testing. And testing, essentially, diagnostic testing underlies what is called a pre-test probability, which is the probability, is the prior belief that an individual has the disease or not. If you conduct testing on somebody who you have a very high pre-test probability, and that result is then positive, will get your probability of assuming that individual indeed has the disease at the highest level. So it basically, prior belief informs the decision making based on your test. And that is true for hypothesis testing, and that is true for diagnostic testing. And so when you think of diagnostic testing, if you go to see a physician and you have a test, you would assume that that test is 100% accurate, right? And the physician is going to tell you, okay, so, okay, you have COVID, you have, I don't know, any other condition. That is not necessarily true. It's a probability that you have this condition because the test turned positive. But the diagnostic accuracy was agreed. I agree, most tests would have a very high diagnostic accuracy, otherwise they're not passing the FDA or whatsoever. Other tests do not. For example, when you diagnose somebody as being diabetic based on one blood glucose sample, that doesn't have to be true. It can just be a random sample, it can be an analytic error, it can be a pre-analytic error. If you, and you know myocardial infarction, or the heart attack, and the way you measure this, you attach an electrocardiogram, and you measure the electrical activity of the heart. And based on the patterns that you see in the EKG, you will diagnose the patient as having a heart attack or not. It's not that easy. Obviously, you do additional testing because you want to make sure that the patient really has a heart attack. So the diagnostic accuracy and the diagnostic predictive value of an EKG is actually considerably low. We're looking at 65%. That's how inaccurate that is as a diagnostic tool, as a standalone diagnostic tool. So you need additional tools to create a pretest probability and additional information to come to a post-test probability that allows you to accurately diagnose a disease. That is Bayesian statistics. That's Bayesian analysis. I have a little bit of a side note here. Any questions on that? So it's basically prior belief, prior probabilities that you carry on in deriving a post-test probability based on what you know beforehand. So whatever you know beforehand, it could be that patient comes in and coughs, it is more likely to have a respiratory infection. Patient can come in and, I don't know, can be out of a sample of 100 people from a diabetes clinic, just because everybody is in a diabetes clinic more likely to have diabetes in the waiting room of a diabetes clinic. Logically, you have a higher probability. Therefore, you will be more likely to diagnose the individual as diabetic. I'm not going to go too deep into whether it should replace hypothesis testing, but that's basically along the lines you need to think. Interesting little side detail, it's actually called Bayesian statistics after Reverend Thomas Bayes, who came up with this in the 17th century. So he was a clergyman and mathematician, and he did the following experiment. So he would stand in front of a pool table and take a ball and draw the ball backwards without looking. So once you do the first ball, and so let's say the first ball has a different color, and then you want to determine the location of that ball on that pool table, and he would take different balls then, roll each of them backwards to approach the initial ball. He wouldn't look, but basically by having an independent assistant giving him information about the location of that ball he rolled to the initial first ball, he would gain slowly information that would allow him then ultimately after 3-4 attempts to hit the first initial ball. He did an analysis of that. So if you repeat this like 100 times, you have, with the law of large numbers, you get a fairly accurate estimate of your probability to know where that ball is. And so if you roll it the first time and you know that you were too much right, and then you roll the second time and now you're too much left, you narrow down your knowledge about the position of the first ball. And based on these experiments, he wrote those experiments down, and he was able to determine that prior belief influenced in a certain way basically the accuracy of hitting that ball. So that was the experiments he did. Does that make sense? Were you able to follow along? I'm trying to explain it with my own words, sometimes a little tricky. But yeah, so that's basically how prior belief system came up, and this is labeled as Bayes' theorem. you will come across this in case you go into the realm of mathematics and statistics. Okay, any questions? All right, that's all I have for today. Have a nice evening and see you on Wednesday for a review of t-distribution.